prior to 1897, you might remember from chemistry that the model of the atom said essentially that every atom is just a solid sphere. Every atom is like a marble or a pool ball. They may be a little bit different. One might be orange and one might be blue, but in the end, we can't break down an atom into anything smaller than an atom any more than we can break down a marble into anything smaller than a marble. Let's fast forward to 1897 and look at an experiment that was performed by J.J. Thomson. You guys, again, from chemistry, might remember this. The model of the atom that Thomson came up with involved something that was smaller than the atom, something that we call the electron, a subatomic particle, the first recognition of a particle that's smaller than the atom. He discovered the electron, and he did that by using a device that we call a cathode ray tube. Now, up until a few weeks ago, in the corner of the room, we had this old TV, this big, old, clunky TV. Some of you guys might still have one in your basement or your bedroom. You can't buy them anymore, but they tended to last a while, so some people still have them kicking around the house. One of the old style TVs are based on this cathode ray technology. A cathode ray is basically, in its most basic form, an evacuated glass tube. Inside that television that used to be in the corner of the room, or maybe that's in the basement of your house, you have this big, heavy, clunky glass tube, and it's evacuated, which means all the air is sucked out of it. There's nothing inside it. But we do attach a wire to one end. Attach that wire to a power supply. Now, this is a bit of a simplification because really we'd have to have what we call a step-up transformer to increase the voltage to a really high value so that we get a big voltage, a big energy per charge over here, but this works. Let's just pretend we have a really powerful battery with a negative terminal, by the way, and a positive terminal that's connected at one end to what we call the cathode. And I know if you take chemistry, you're going to not like this. If you take chemistry, you're going to want to call that the anode. Okay? We call it the cathode here. Electrons go from the anode to the cathode. Call this the anode. Aren't the electrons going towards the anode this time? If they leave the cathode, go towards the anode? Well, kind of. But you could also kind of think of it going this way, right? They're going from around here, from the anode to the cathode. Whatever. I'm sorry if it's confusing to you, but it is what it is. Okay. We call this in physics, we call this the cathode, we call this the anode. Prior to 1897, maybe for about 50 years prior to 1897, people had actually been using these cathode ray tubes and noticed that something was leaving this cathode, going toward the anode, skipping right past the anode, and then striking the screen right here. People had seen this. These mysterious cathode rays. Nobody really knew what they were, though. Some people guessed or hypothesized that maybe they're particles. Maybe they're even charged particles. Maybe it's some form of electromagnetic radiation. We don't really know. But then in 1897, advances in technology of vacuum pumps to get the air sucked out of it better, led to Thomson being able to determine what these mysterious cathode rays really were. Here's how he did it. Down here, close to the end, close to the screen, this would be the screen of your television right here. It is, by the way, painted with a phosphorescent coating so that when these cathode rays strike it, it glows. And that's why the TV forms a picture, because these beams of electrons, or cathode rays, are going through the cathode ray tube, strike the screen in a specific spot, and cause it to glow, forms a picture. These cathode rays striking the screen, people had seen it for years and years and years, didn't know what it was. But Thomson says, you know what, I want to figure out what these things are. I want to figure out what these cathode rays are. So he introduces a magnetic field right here. That magnetic field causes these mysterious cathode rays, again, whatever they are, causes these cathode rays to be deflected. And he looked at this and said, hey, I kind of know what these are. These cathode rays must be negatively charged particles. How do we know this? Because it's only negatively charged particles that are deflected this way in a magnetic field, right? Hand rule for deflection. Thumb in the direction of the particle, fingers in the direction of the field, palm points toward the bottom of the page. Now, some of you might be thinking, if we didn't know about the electron, then how did we know how electrons responded in a magnetic field? We didn't know about the electron, but prior to Thomson, we knew about charge. Remember Ørsted in 1819? Like almost 80 years before this, discovered that moving charges generate a magnetic field. We knew lots about charge prior to this. We just didn't know where it came from. We didn't know that electrons gave us charge. We knew, it was well established, that negative charges would be deflected by a magnetic field, and we could predict which way they were deflected. So he introduces this magnetic field and finds that these particles are deflected downwards in a circular path. Therefore, they must be negatively charged particles. Didn't know anything about the subatomic nature of them yet, but just that they were negatively charged. So now he says, look, I've observed that they're deflecting in a certain direction in a magnetic field. I know that they're negatively charged particles. Let me try to do a little bit of an analysis on this. He knows that charged particles going in a magnetic field go in a circle. So let's set Fc equal to Fm. mv squared over r equals qvb. This isn't new, is it? This is 2 units ago. Nice little review of what we did in our magnetism unit. V's cancel, one of the V's cancels at least. And I'm left with mv over r equals q times b. Says, well, let's plug in some numbers and see what we get here. Says, I know the value of B. Listen, he's the one that put the magnetic field there. He can control whatever it is. He knows the value of B, the magnetic field. He knows the value of R. This is a little bit tougher, but he can look at where doesn't know their electrons yet, right? Where the cathode rays strike the screen and determine the radius of the path from that. So he gets R. But he doesn't know what M is. He knows that these are negatively charged particles, but he doesn't know how heavy they are. He doesn't know what V is. How fast are they moving? Pretty fast, but I don't know exactly how fast. Q, he doesn't know what Q is either. So he's got an equation, 5 variables. He knows what 2 of them are, and he doesn't know what 3 of them are. Doesn't lead us to much, right? Doesn't tell us much. 3 unknowns in the same equation. Right, Dylan? So here's what he does. He introduces another little section here where we've got a magnetic field that causes a magnetic force on these particles downwards. Thumb, fingers, palm points downwards. But in the same place, he creates an electric force caused by an electric field, which is caused by 2 parallel plates. An electric force on these particles that's upwards. Now, if these particles, these negatively charged particles that we're calling cathode rays, are going too fast or too slow, then one force will be bigger than the other, and they're going to be deflected upwards or downwards. We don't care about those ones. Let them go. They're deflected upwards, deflected downwards. They're irrelevant to us. We care about the ones that are going at just the right speed. Just the right speed. The right speed such that the magnetic force downwards will balance the electric force upwards. For those particles that are going at the right speed to balance those forces, those particles will end up going straight through. And if they go straight through, then they enter this last section over here that I sometimes call the main chamber at a certain speed that I can then plug into this equation. Let's analyze this section, though, that we sometimes call the velocity selector. We say Fe equals Fm. The electric force is Q times the electric field, and the magnetic force is QVB. Q's cancel. I get V is equal to electric field over magnetic field. Let's get that value. We know what E is. We know what V is. Let's get the value of V. Let's get the value of the speed. And then let's plug it into here. And now we've got one more variable. We kind of tipped the scales a little bit now, right? We knew what B and R were. Now we know what B and R and V are. So now we have only two unknowns there. Charge and mass. No matter what Thomson does, he can't figure out what Q is or can't figure out what M is. But he did do something with this that led to the discovery of the electron. Let me give you a little analogy first, though, to help you to understand what he did. Someone knocks on the door and looks at Ben and says, Ben, how old are you? Ben says, I'm not telling you how old I am. It's kind of weird. And then he looks at me and says, Mr. Dickie, how old are you? And I'm like, I'm not telling you how old I am. He says, well, can you give me something? And Ben says, well, Mr. Dickie's twice as old as I am. The ratio of Mr. Dickie's age to my age is 2-to-1. The guy walks away and says, well, I wanted Ben's age and I wanted Mr. Dickie's age. I don't have either one of those, but I know something that I didn't know before. I know that Mr. Dickie is twice as old as Ben is. I know the ratio of their ages, right? Which is not as good as knowing their ages, but it's better than nothing. Thomson couldn't find Q and he couldn't find M, but what he did do is found the ratio of Q to M. So he takes this equation and rearranges it. M goes down by dividing, B goes down by dividing. The ratio of Q to M is V over B times R. And he calculates that knowing the value of V from the velocity selector, knowing the value of B and R from the main chamber. And when he does that, he gets a value that's about 1.76 times 10 to the 11 coulombs per kilogram. You don't need to memorize that number, by the way. Why is this number so important? Because it's the biggest charge to mass ratio that had ever been observed. People had tried measuring charge to mass ratios of different things. Here's an atom, here's an ion, whatever. Here's charge to mass ratio of this and that, whatever. They were all smaller than this number. Why is that important? If this charge to mass ratio is bigger than any other charge to mass ratio that exists, then that must mean the mass is, if Q over M is big, then that must mean M is small. If this number is bigger than anything else ever measured, then that mass must be smaller than anything else ever measured. It's smaller than the mass of an atom. If the mass of these cathode rays are smaller than the mass of an atom, then these particles must be smaller than atoms. Now we've got negatively charged particles that are smaller than atoms, or negatively charged subatomic particles. Does that make sense? That's the discovery of the electron, right there. He observed that they're negatively charged particles because of the way they deflected in the magnetic field, and he calculated the charge to mass ratio, got such a big number that the mass must be so small that the only viable option must be that they're subatomic negatively charged particles. Hence, discovery of the electron. Now, we've done an analysis here of two sections of this cathode ray tube. We call it the velocity selector or the main chamber. There's a third one right here that I sometimes call the acceleration chamber. It's not very often that we have to deal with that one, but if we do, we know what to do. These are charged particles that are speeding up. These are electrons as we now know them, electrons, right? We're not calling them cathode rays anymore because we know they're electrons now. These are electrons that speed up. What do we do when charged particles speed up? What do we always do when charged particles speed up? We treat it like a car going down a hill. Top of the hill, the car would have potential energy. Well, in this case, it would be electric potential. At the bottom of the hill, the car would have kinetic energy. So we've got the acceleration chamber, where it's an energy analysis. We've got the velocity selection chamber, where Fe is equal to Fm. And then we've got the main chamber, where Fe is equal, where Fc is equal to Fm. Why didn't Thomson just get V from here? Like he got V from this velocity selector, right, to put into the main chamber. Why didn't he just get it from here? Well, there's a couple of reasons why he didn't get it from there. One, because when you solve for that speed, that's the maximum possible speed the particles can be moving. If the energy conversion is 100% efficient, then that's how fast they're going. But if you lose a little bit, then they're not going quite that fast. So we're not really finding the actual speed, we're finding the maximum speed. We want the actual speed. Secondly, he didn't know Q or M. In order to use that to find speed, you need to know what Q is and you need to know what M is. There's this whole point, right? He didn't know what Q and M were. I'll tell you what, 9.5 times out of 10, you're doing a cathode ray tube problem, it's going to be this, or a combination of those. This, or a combination of those. So this is just a little summary of his conclusion, right? Thomson measured the charge to mass ratio of the electron. What did he get? Again, you don't need to memorize this number. But it was really, really big. So big that the mass had to be really, really small. So small that they were smaller than the mass of atoms, which means that they had to be subatomic particles. First discovery of subatomic particles. So then Thomson comes up with his little model of the atom, which is so wrong, but still so much better than the solid sphere model of the atom, because at least there's something inside. There's the sea of positive charge. It's kind of like a harbor. You go to Vancouver and there's the harbor, and then the water would represent the positive charge in the atom. But then you got these boats floating around, moving around in the water. Those would be the electrons that are not orbiting or anything like that, just moving around, just floating around in this sea of positive charge. It's not even close to the model of the atom that we have now. There's no nucleus, there's no orbiting around. Like it's so far off of what we currently accept to be our model of the atom, but at least there's something subatomic now. It's not just the atom itself. That's why we talk about it, because it's still a big step forward. Okay, let's have a look at an example here, okay? Chapter 15 we're in now, so if you don't have that downloaded, then grab a copy of that. Page 756, it says, a beam of electrons passes undeflected through a 0.5 Tesla magnetic field combined with a 50 kilonewton per coulomb electric field. The electric field, the magnetic field, and the velocity of the electrons are all perpendicular. How fast are the electrons traveling? This is a cathode ray tube problem. What section of the cathode ray tube is it, though? We have beam of electrons passing undeflected through a magnetic and electric field. Which section would it be? The first, the second, or the third? If we've got particles going undeflected through an electric and a magnetic field. It's the second one, right? There's two things that tell us it's the second velocity selector there. One, you get both an electric and a magnetic field. Two, the word undeflected. Both of those things tell us it's the second chamber. So let's say, in this problem, let's say Fe equals Fm. That's what we do for the velocity selector. Let's say Q times E is equal to QVB. Charges cancel. He didn't know what the charge was, but it didn't matter that he didn't know what the charge was because it disappears from the equation. Rearrange to solve for V, and we get electric field over magnetic field. And we know the values of both of those. E is 50,000 newtons per coulomb, or 50 times 10 to the 3, and B is 0.50. I think when you do the math there, I think it works out to be 1.0 times 10 to the 5 meters per second, I believe. Which is a pretty typical speed for an electron, especially in the cathode ray tube. All right, have a look at these three questions, please, on page 756. When you do, I mean, clearly they're all going to be cathode ray tube problems, right? But stop and think about not just cathode ray tube, but think about which section of the cathode ray tube. Really, we haven't learned to solve one type of problem here. We've just learned how to solve three types of problems. So you've got to identify in every cathode ray tube question you get which section it is, and then do your thing. Don't just say, oh, it's a cathode ray tube, I'll do my thing. Say, it's a velocity selector, I'll do my thing. Or it's a main chamber, I'll do my thing. Okay, figure out which section it is first and then do it. All right, let's have a look at one more example then. This one looks, look at the picture, it looks a little bit more complicated. Page 758, it says, when a beam of electrons accelerated to a speed of 5.93 times 10 to the 5 meters per second, directed perpendicular to a magnetic field of this value. I'm going to circle that because it's strange units. They travel on a circular path with this radius. What's the charge to mass ratio for the electron? Which section of the cathode ray tube is this? The charged particles are going this speed through a magnetic field going in a circle. We want to find the charge to mass ratio. Look at my picture. Which section are we dealing with? 1, 2, or 3? Yep. It's going to be 3. When we have an electric field and a magnetic field, it's the second section. When we have just a magnetic field and when it says it's going in a circle, it's going to be the third chamber here. And this is exactly what Thomson would have done, right? He looked at the third chamber and he wanted to find the charge to mass ratio. So he says FC is equal to FM, just like you guys did back in Unit 2. Sorry, Unit 3, I should say. MV squared over R is equal to QVB. We'll cross off the V's. We got MV over R equals Q times B, and then we'll rearrange it to solve for Q over M. The M has to go down, get it on the bottom, and the B has to go down. So I end up with Q over M is equal to V over B times R. Or Q over M is equal to 5.93 times 10 to the 5 divided by 100 times 10 to the minus 6. It's 100 Tesla, 100 microtesla, I should say. And R is going to be 3.37 times 10 to the minus 2. Or maybe we'll just say 0.0337. Okay, let's figure out what that is. On our calculators, let's say 5.93 times 10 to the 5 divided by, use some brackets on the bottom here, 100 times 10 to the minus 6 times 0.337. And when we do that math, it works out to be, look at that, 1.76. I made a mistake there. That should be that's 0.0337, isn't it? Not 0.337? How did I know when I did that I made a mistake? What did I tell you the charge to mass ratio of an electron should be? 1.76 times 10 to the, not that you need to remember this number, but 1.76 times 10 to the 11 coulombs per kilogram. And I just got 10 to the 10, so I knew there was a mistake there somewhere. It's a Thomson gun, right? Big number. Such a big number that mass must be a small number. Such a small number that it was smaller than the mass of an atom. which means it's got to be subatomic. Let's have a look now at the 3 questions that go with those on page 758, please.